Hey everyone, welcome back to Chem Story. Ever wondered how chemists make complex three-dimensional structures easy to read? That's where Fischer projections come in. They're super helpful for visualizing molecular connections. Today, we'll break down how to use them correctly, step by step. Let's get started. A Fischer projection is basically a two-dimensional way to represent a three-dimensional molecule, and it's especially handy for carbohydrates and amino acids. The whole point is to simplify these complex structures while still keeping the stereochemistry clear. Take D-glucose, for example. When you look at its Fischer projection, you'll see how the atoms are arranged in a way that makes it much easier to compare stereochemistry. It's all about keeping the layout clear and straightforward. Alright, let's talk about how to read Fischer projections. Vertical lines, those show bonds pointing away from you, like they're going into the plane. Horizontal lines, those are the opposite. They represent bonds coming toward you, out of the plane. It's a simple way to visualize three-dimensional structure on a flat surface. Here's an important rule for setting up Fischer projections. The main carbon chain always goes vertically, and at the top, you'll find the most oxidized carbon, usually something like an aldehyde or a ketone. That's why Fischer projections are super useful for monosaccharides. They make it really clear how different sugars relate to each other. Alright, now that we've got the basics down, let's break it down step by step and learn how to draw them. When you're converting a tetrahedral structure to a Fischer projection, the main goal is to keep the bond positions consistent, no matter how you're looking at the molecule. Here's the trick. Hold the tetrahedral carbon so that two bonds point forward and two point backward. When you flatten it out, the forward bonds become horizontal and the backward bonds become vertical. This rule works no matter which angle you're viewing from. That's why even if Fischer projections look a bit different from different perspectives, they still represent the same molecule. Nailing the positioning is crucial for accuracy, so make sure you get that part right. Alright, let's break down how Fischer projections relate to stereochemistry, specifically how to figure out R and S configurations. The key is knowing how the bonds are positioned. In Fischer projections, vertical bonds point away from you, while horizontal bonds come toward you. Here's the tricky part. The lowest priority group, usually hydrogen, often ends up in front. Moving it to the back every time can get pretty tedious. But here's a shortcut. Assign priorities as usual without moving the hydrogen. If the path from 1 to 3 goes clockwise, it might look like R, but since hydrogen's in front, it's actually S. If it goes counterclockwise, it looks like S, but again, with hydrogen in front, it's really R. So just remember, if hydrogen's facing you, flip the result. It's a quick way to get the right answer without a lot of rotations. In this case, the sequence moves counterclockwise, so when you flip the result, you get the correct R configuration. Alright, now that we've nailed down R and S determination, let's talk about how transformations affect chirality. One important point, a 180-degree rotation in a Fischer projection doesn't actually change the molecule's configuration. Even though it looks like the substituents have swapped places, their relative positions in three-dimensional space are still the same, which means the stereochemistry stays intact. For example, let's say we assign priorities as A highest to B to C to D lowest. If the chiral carbon in the original Fischer projection on the left has an S configuration, rotating the molecule by 180 degrees still leaves us with that same S configuration. So this confirms that a 180-degree rotation is totally valid and doesn't mess with chirality at all. Now, unlike a 180-degree rotation, a 90-degree rotation just doesn't work. It actually changes the molecule's stereochemistry. Here's why. After a 90-degree turn, the substituents end up in the wrong places, which means the RS configuration gets flipped. That's why a 90-degree rotation is considered invalid. Here's a neat trick for transforming Fischer projections without messing up the stereochemistry. Keep one substituent fixed while rotating the other three. In the image, for example, the top substituent, A, stays in place while the other three move around. Even though the structures might look different after rotating, the absolute configuration, in this case S, doesn't change. This method is super handy when you need to rearrange Fischer projections, but still want to keep the stereochemistry accurate. One thing you definitely can't do in Fischer projections is swap the two horizontal substituents. Why? Because doing that creates an enantiomer. Take a look at the image. If you switch C and D, the RS configuration gets flipped, basically turning the molecule into its mirror image. So just remember, swapping horizontal groups isn't allowed, since it changes the molecule's stereochemistry. Alright, let's take a closer look at what Fischer projections really show. In a Fischer projection, we usually draw the carbon backbone as a straight vertical line. But in reality, it's not flat. The carbon-carbon bonds are slightly offset, giving the backbone a kind of cylindrical, helical twist. That's why converting between Fischer projections and three-dimensional skeletal structures can be tricky. The spatial arrangement doesn't always match up. Since the projection doesn't capture how the chain actually wraps around in space, it can be hard to picture the real shape. So how do we accurately switch between three-dimensional structures and Fischer projections? Let's break it down step by step. Alright, let's go over how to convert a skeletal structure into a Fischer projection. There are three main methods, and you can choose the one that works best for you. The first method focuses on rotating bonds to match the cylindrical shape typical of Fischer projections. You start by rotating the molecule into an ellipsed conformation, then flatten it onto a plane, making the vertical chain the carbon backbone and the horizontal bonds point forward. But here's the catch. It involves a lot of bond rotations, which makes mistakes pretty common. That's why I don't really recommend this method. There are definitely more reliable ways to do it. Here's another method. It's a bit more methodical and focuses on using R-S configurations. Start by figuring out the R-S configurations for each chiral center in your skeletal structure. Then, use those configurations to directly build the Fischer projection, placing the substituents accordingly. The downside? It can be time-consuming since you have to determine each configuration one by one. Plus, a single mistake with the configurations or placements can throw off the whole projection. So, while it's more precise, it does take extra effort and carries a higher risk of errors. Alright, the third method for converting a skeletal structure into a Fischer projection is pretty straightforward. This one directly uses the positions and orientations of the substituents from the skeletal structure itself. Instead of going through complex rotations or R-S configurations, you just map the substituents directly onto the Fischer projection. It's a more direct approach, so it can save time compared to the other methods. But you still need to be careful to keep the spatial orientation accurate when transferring the substituents. It's simple, but precision is key. To make this method work systematically, we start by picking a fixed reference point. The easiest way to do this is to take the rightmost substituent in the skeletal structure and place it at the top of the Fischer projection. This spot becomes our starting point. From here, we'll position the other substituents step by step. It's a simple way to keep things organized and accurate. Next, we draw an imaginary horizontal line right through the middle of the carbon chain. This line acts like a reference point, helping us figure out which substituents are above and which are below it in the skeletal structure. It's a simple trick to make sure we place them correctly when drawing the Fischer projection. Just think of it as a guide to keep everything in the right place. Alright, let's go ahead and place the substituents directly into the Fischer projection. If a substituent is above the horizontal line, put the dash bond on the left side of the Fischer projection, and if it's a wedge bond, place it on the right side. Simple as that. In this structure, the substituents connected to carbons 2 and 4 have wedge bonds. That means they'll show up on the right side of the Fischer projection. Now, for the substituents below the horizontal line, it's the opposite. Dash bonds move to the right side of the Fischer projection, while wedge bonds go to the left. Just remember, it's a simple flip from how we handled the ones above the line. So in this case, the wedge bond on carbon 3 will end up on the left side of the Fischer projection. And the dash bond on carbon 5? That'll go on the right side. Just follow the pattern, and you'll keep everything in the right place. Alright, the final step is to position the remaining hydrogen atoms to complete the Fischer projection. This method is pretty intuitive because you're just following the original orientations from the skeletal structure to place each substituent correctly. Alright, now let's talk about how to go the other way, converting a Fischer projection back into a skeletal structure. It's basically the reverse of what we did earlier when we turned a skeletal structure into a Fischer projection. Start by arranging the vertically drawn carbon backbone into an ellipsed conformation, kind of like wrapping it around a cylindrical shape. Once you've got that set up, rotate the bonds into a more stable zigzag conformation to complete the structure. Since this method involves a lot of bond rotations, you'll want to make careful adjustments to make sure everything lines up correctly. Here's another way to convert a Fischer projection into a skeletal structure, this time using RS configurations. Instead of worrying about rotating bonds, you just focus on directly assigning the stereochemical configurations. It's a more straightforward approach, especially when dealing with complex molecules where bond rotations can get messy. First, figure out the RS configurations for each chiral center in the Fischer projection. Next, draw the skeletal structure in a zigzag pattern and match the RS configurations to each chiral center as you go. This method works great when rotation isn't practical, but you've got to be precise. A single mistake in assigning or applying the configurations can throw off the whole structure. So, double-check your work to keep it accurate. An even simpler way to convert a Fischer projection into a skeletal structure is to just assign the substituents directly based on where they're positioned. Instead of going through complex configurations or rotations, you just look at the Fischer projection and place each substituent in the skeletal structure right where it belongs. It's a pretty intuitive method, and it saves time since you're not worrying about complex transformations. To get started, find the topmost substituent in the Fischer projection. Then, place it at the rightmost position in the skeletal structure. This spot acts as your reference point, making it easier to position the rest of the substituents correctly. Next up, draw an imaginary horizontal line right through the middle of your skeletal structure. Think of this line as a guide. It helps you figure out which substituents go above and which go below. Alright, now let's figure out how to place substituents from the right side of a Fischer projection into a skeletal structure. Here's the rule. If a substituent is above the horizontal line, you draw it as a wedge bond in the skeletal structure, which means it points forward. If it's below the line, it becomes a dash bond, pointing backward. Alright, so in this case, we've got substituents on the right side of the Fischer projection, specifically on carbons 2, 4, and 5. The hydroxyl groups on carbons 2 and 4 are above the horizontal line, which means we'll represent them as wedge bonds in the skeletal structure, pointing forward. On the other hand, the hydroxyl group on carbon 5 is below the line, so it'll be drawn as a dash bond, pointing backward. Now that we've covered the right side, let's move on to the left side of the Fischer projection and see how those substituents fit into the skeletal structure. Here's the rule. If a substituent on the left side is above the horizontal line, you'll draw it as a dash bond in the skeletal structure, meaning it points backward. If it's below the line, it becomes a wedge bond, pointing forward. Just keep this pattern in mind, and you'll get the placement right every time. Alright, in this case, the substituent on carbon 3 is on the left side of the Fischer projection. Since the hydroxyl group is positioned below the horizontal line, we'll draw it as a wedge bond in the skeletal structure, pointing forward. Okay, we've covered a lot today. We went through what Fischer projections are, how to read them, and how to convert them to and from skeletal structures. The real trick to mastering these conversions? Practice. The more you work with Fischer projections, the more natural they'll feel. That's it for today's lesson. Hope this breakdown helped make things a lot clearer. Thanks for sticking with me, and I'll see you in the next one.